Hi everyone, welcome back. This is lesson 31 continued, or lesson 31 part 2. We've talked about simplifying square roots, and what we will now do is learn about multiplying them together as well as dividing them. And the last topic that we'll see, which is related to dividing, is something called rationalizing denominators. So we'll start with multiplying. So this slide says multiply and simplify. Use the product rule. Okay, we learned that already. It says the square root of a times the square root of b is equal to the square root of a times b. When we use this rule, we're going to be really using it in reverse. Rather than multiplying, we will also be using it to factor. So let me rephrase that. We'll be using it in both directions. Let's say that, okay? So we will be multiplying numbers together, and then later at the end, we might use the product rule again to factor them apart. Let's take a look at number 1. The square root of 10 times the square root of 15. Okay, so we're going to multiply these together first and then simplify. The square root of 10 times the square root of 15. Well, if I put those together, that's the square root of 10 times 15, which is the square root of 150. Okay, so that's the multiplying part, but we also need to simplify. So now that I just multiplied and got 150, now I need to go back and break down the 150. I'm going to show you a couple of different ways of doing this. I've been focusing on looking for perfect squares. Sometimes that's a little more challenging though. So I'll show us a couple different ways of going about this. But first I'll show the way that I already showed in the earlier video. So I'll have a little list of perfect squares going. Square root of 4, what else? Square root of 9, square root of 16, square root of 25. Those are just the really common ones. The square root of 25 does go into the square root of 150. So if I divide 150 by any of these numbers, let's just try. 150 divided by 4, nope, that doesn't work. 150 divided by 9, nope. I'm getting decimals. 150 divided by 16, no. 150 divided by 25, yes. It does work because when I divide 150 by 25, I get a nice whole number 6. So let's make our little factor tree. The square root of 150 can be written as the square root of 25 times the square root of 6. The reason why this will help us to simplify is because the square root of 25 is just 5. So essentially I'm kind of pulling out a perfect square. So my answer becomes 5 times the square root of 6. This is our final answer. Now, I mentioned there's another way of doing this. Let's take a look at what that is. Because sometimes it's not so easy or simple to just identify a perfect square that goes into a number, especially when they get pretty big. So let's see another strategy we can use. All right, so if we're dealing with the square root of 150, maybe you don't know a perfect square that goes in, or you can't think of one and you're just feeling stuck. So here's what you can do. You can still make a factor tree, just break it down in any way that you want. So remember how we got the number 150? We got it from doing 10 times 15. Let's just do that. 10 times 15. Okay, I know they're not perfect squares. That's okay, keep going. How can I break down the number 10? All right, well, how about 2 times 5? Again, they're not perfect squares, it's okay. And then 15, I can break that down into, let's see, 5 times 3. So essentially, I've made a factor tree where I've gotten all the way down to just prime factors. So at the end of my tree, here's what I have. The square root of 2 times the square root of 5 times the square root of 5 times the square root of 3. Here's what we can look for. We're looking for perfect squares, but here's what those perfect squares can look like. We're going to look for pairs of numbers. In other words, when you look at those prime factors down below, do you see any that are appearing twice? Yes, the 5s right here. So that was kind of our perfect square in disguise. Now let me show you what that means. If I put this together, the square root of 5 times the square root of 5, that's just 5. Here's why. If I do the square root of 5 times the square root of 5, that's the square root of 25, which is 5. But you don't even really need that square root of 25 in that middle step. So let me write that in one additional way here. I'm going to write it using an exponent. The square root of 5 times the square root of 5. This is really the square root of 5 squared. And when you take the square root of a perfect square, the square root and the 2 exponent cancel out, and you're left with just that number by itself, 5. So however you want to think about it, the square root of 5 times the square root of 5 becomes 5. So why does that matter? Well, here we go. The 5 gets to be outside in our final answer. Now, what are the square roots that we were left over with? We still had that square root of 2, and we still had the square root of 3. We just need to put those back together now. Okay, so here's what we get to do. Our final answer is 5 times the square root of, if we do 2 times 3, we get 6. So compare this method to what we had done earlier. Remember earlier what we did is the square root of 150, broke it down into the square root of 25 times the square root of 6. And that led to 5 square root of 6. I still like that method better. I think it's cleaner and shorter and more efficient. However, making a different kind of factor tree just all the way down to prime factors without worrying about perfect squares is still a valid option. So I did want you to see a couple of ways of getting there. But I hope you can also see that you need to show some kind of work. Right, so if you just had the square root of 10 times the square root of 15, and then you just wrote 5 square root of 6 for your answer, that's not enough. I need more than that, okay? You need to show some intermediate steps of some kind, and hopefully I've modeled a couple ways you can do that. Okay, let's get back to our notes, and we'll take a look at number 2, which involves some larger numbers. Okay, so number 2, we're multiplying and simplifying. Number 2 is the square root of 75 times the square root of 24. Okay, so before what we had done is multiplied first and then simplified. Well, this is going to be pretty big, right? So 75 times 24 is 1800. I mean, I guess that's fine. We could do that, right? So I guess we could do this in a couple of ways. We could multiply first the square root of 1800. And then we could break that number down. That would be okay. Let's try it that way. And then just like last time, I am going to show us a sort of alternate way to do this. What we can do is we can actually simplify the square root of 75 first, and we can simplify the square root of 24 first. So I'll show you both and you can decide which you prefer. So I'm going to go with multiplying first and then simplifying, even though it's a big number. 75 times 24 is 1800. Let's try to break this down using perfect squares. Okay, so I'm noticing the 100 part of this, the 2 zeros. So that's what I'm going to use to break this down. So if I'm trying to factor 1800 using perfect squares, the first one I think of is 100. So I'm going to break it down like this. The square root of 100 times the square root of 18. The square root of 100 is 10. So I have 10 times the square root of 18. Okay, that's not fully simplified because the square root of 18 can be broken down more. There's still a perfect square in there. It's kind of like when we factor, we needed to factor completely. Sometimes that meant you took out a GCF and then you also had to do the difference of perfect squares or something like that. There were more than one type of factoring you needed to do, more than one step. That's kind of what's happening here. I broke it down, but I can break it down more. So again, I multiplied 75 times 24 and got 1800. We're working on the square root of 1800. I broke it down into the square root of 100 times the square root of 18. The square root of 100 became 10. So now I have 10 times the square root of 18. Now let's keep going. 18 is a multiple of a perfect square, which is 9. So I can break that down more. This is the square root of 9 times the square root of 2. The square root of 9 is 3. So putting all the pieces together, I have this 10 on the outside. Now I also have a 3, and then I have this square root of 2. So putting it all together, here's what we get. 10 times 3 times the square root of 2. The 10 times 3 becomes 30. So our final answer is 30 times the square root of 2. Here's what this means. 100 wasn't the biggest perfect square that went into 1800. I could have actually used 900. So the square root of 900 is 30. I mean, that was not in our list. I didn't even really realize that. So that's okay. A lot of times this is what happens. You break it down and then you realize you can break it down more. Okay, so we got to our final answer of 30 square root of 2. I told you I was going to show you another way to avoid that such a large number, and I'm going to show you that right now. So let's take a look at another way to simplify, especially when our square roots are kind of on the bigger side, like what we have here. So the square root of 75 times the square root of 24. Rather than multiplying first, we're going to simplify first. So let's look at each square root separately. Let's start with the square root of 75. This is a multiple of 25, which is a perfect square. So I'm going to break this down into the square root of 25 times the square root of 3. That becomes 5 square root of 3. Okay, what about the 24? Well, let's break that down. Let's see, what's a perfect square that goes into 24? How about 4? 24 is 4 times 6, so I'm writing the square root of 4 times the square root of 6. The square root of 4 is 2, and then I have the square root of 6. So let's look at all the pieces we have so far. So we have 5 square root of 3 times 2 square root of 6. We're going to rearrange a little bit right now. Take the whole numbers on the outside, the 5 times the 2. We're going to put those together. And then let's take the square roots, the square root of 3 times the square root of 6. Let's put those together. So we're just reordering a little bit. So here's what we have so far. 5 times 2 times square root of 3 times square root of 6. Now let's start putting things together. 5 times 2 is 10. The square root of 3 times the square root of 6 is the square root of 18. This should look familiar. We just saw this, right? From here to the end, we did this already, right? 10 square root of 18. We're on our way, but we can keep going because the square root of 18 can be simplified. So I'll just redo that again. The square root of 18 can be written as the square root of 9 times the square root of 2. This is now 10 times 3 square root of 2, because the square root of 9 becomes 3. And then finally, 10 times 3 is 30. So we still end up with the same answer of 30 square root of 2, but we never had to deal with such a large number. We chose to do some breaking down first, some rearranging. We still had to do it in a couple of steps. So it's up to you. It's going to depend on the number, but consider when you're multiplying, see if you can simplify each radical first, and that might make the rest of the problem easier. All right, so those were 2 multiplying examples. Let's go back and take a look at some dividing examples. So our next slide says divide and simplify. Use the quotient rule. The square root of a over b equals the square root of a over the square root of b. We're going to use this rule in both directions. Sometimes we'll use it to split up a fraction. Sometimes we'll use it to put a fraction back together. So we'll see an example of each of those. Number 1, the square root of 245 over the square root of 5. Okay, 245 is a large number. I don't know what perfect squares go into it. So before we dive into that, let's see if we can reduce this at all or simplify this at all. So we're going to use the quotient rule kind of in reverse. So I'm going to use the fact that a square root over a square root, it can be combined into one big square root with a fraction underneath. So the original problem again is the square root of 245 over the square root of 5. I can rewrite it as the square root of 245 over 5. Now, 245 ends in a 5. I'm pretty sure this is going to work if I divide by 5. So 245 divided by 5 is 49. So now I'm going to rewrite this. Instead of the square root of 245 over 5, I just divided 245 by 5 and got 49. So now I'm writing the square root of 49. So suddenly I don't have a fraction anymore, and suddenly this becomes pretty nice. I can simplify this. The square root of 49 is 7. That's it. Okay, so I divided by 5 first and then was able to simplify more from there. The other way we could have done it is we could have broken down 245. It would have probably taken a while to realize that the perfect square that goes in is 49. We'd have to go pretty far down our list before we realize that. So if you simplify the square root of 245, that would have been 7 square root of 5 over the square root of 5, and then those square root of 5s just cancel out. I like our first way better. So if it's possible to divide first, I think you're going to have an easier time. Okay, let's look at number 2. This one is different. This one is a square root, and under the whole square root is one single fraction, 25 over 121. Actually, we have talked about this already, but that's good to review. We're using the quotient rule in the original direction, which says we can split this apart into the square root of the numerator over the square root of the denominator. So in this case, it's the square root of 25 over the square root of 121. The square root of 25 is 5. The square root of 121 is 11. So our final answer is 5 over 11. Okay, so two different division problems. They're essentially fraction problems. Whenever you're starting a problem like this, see if the square roots are separated, try putting them together. If they're together, try separating them. And a lot of times things will simplify pretty nicely. All right, and that brings us to our last couple of pages here, or our last couple of slides, excuse me, where we're going to see a different kind of dividing situation where it doesn't simplify quite so nicely. And we're going to do something called rationalizing denominators. So just to go back a second here, see this number 2 that we just did? The denominator was the square root of 121, which was just 11. 11 is a rational number. So the denominator was already rational. I didn't have to do any extra step to make that happen. Sometimes we will need to do an extra step to make that happen, and that's what this next little section will be. So first, we're just kind of reviewing what does it mean, or when is a radical in simplest form? There needs to be no radicals in the denominator. Oops. No fractions in the radicand, and that might be a new word. The radicand is just the number under the radical. So no radicals in the denominator, no fractions under the radical. So we don't want to leave an answer where there's a fraction under a radical. We should always simplify. And finally, radicals have been broken down or simplified as much as possible. Okay, let's get into rationalizing denominators. What does that mean? Okay, so to rationalize the denominator of a fraction with a square root denominator, here's what you do. Multiply the numerator and denominator by that square root. Okay, what square root? Oh, the one from the denominator. Now, if you're multiplying the numerator and denominator by the same thing, you're essentially multiplying by a form of 1, right? The denominator becomes the square root of a perfect square. So we simplify. And then reduce at the end if possible. Let's take a look at some examples that have been done for us. Okay, so here's the first one. the square root of 10 over 3. First, notice how it's been split apart into the square root of 10 over the square root of 3. Now that by itself, that can't be simplified. I can't break down the square root of 10 into perfect squares. I mean, I can do 2 times 5, but that doesn't help anything. The square root of 3 can't be simplified either. So notice in red right here, this is where we're multiplying the numerator and the denominator by the square root that was originally in the denominator. So again, we had the square root of 10 over the square root of 3. And we're multiplying by the square root of 3 over the square root of 3. That's a fancy form of 1, by the way. Just a reminder, that's why that's even allowed, okay? So the square root of 3 over square root of 3, it's just 1. It's not changing the value of our answer. It's going to look different, but it's still going to be technically equal to what we started with. So why do we do this? Let's find out. Okay, so in the denominator, because that's what we're focusing on, here's what's happening. The square root of 3 that was already there times this new square root of 3, that becomes the square root of 9, which is 3. Okay, so now suddenly the denominator 3 is rational at the end. That was the whole point. We wanted the denominator to be a nice rational number. In other words, we don't want it to be a radical in the denominator. Meanwhile, the numerator, anything goes there. So just kind of simplify and see what happens. So in this problem, the square root of 10 was in the numerator. We multiplied by the square root of 3, and then we got the square root of 30. If you try to break down the square root of 30, that's a good idea, but there's no perfect squares that go into 30, so we would be done at this point. The final answer is the square root of 30 over just a whole number 3. And that whole number 3 is rational at the end of the problem. Okay, one more. This one's a little harder. And then, and again, these are already done out for you in the notes. Then we'll do some kind of together from scratch. So here's the next one, 21 square root of 2 over 5 square root of 7. The goal is to rationalize the denominator. So focus on what is the radical in the denominator in this problem. What is the square root in the denominator? It's just that square root of 7. That's what we need to get rid of, kind of. So that's what I'm going to multiply by in the numerator and denominator. So again, the original problem, 21 square root of 2 over 5 square root of 7. We're going to multiply by the square root of 7 over the square root of 7. Now let's multiply across. Let's start with the denominator here. 5 square root of 7 times square root of 7. Okay, those two square roots together, square root of 7 times square root of 7 is square root of 49, which becomes 7. So in the denominator, I now just have 5 times 7. I realize that that's 35, but I'm leaving it factored for a reason. We'll come back to that. Meanwhile, in the numerator, we had 21 square root of 2 times square root of 7. Okay, we're multiplying the square roots together. 2 times 7 becomes 14. So here's where we are. In the numerator, we have 21 square root of 14 over 5 times 7. Now we just reduce. So the reason why I left the 5 times 7 separated is because the 21 in the numerator can reduce with the 7 in the denominator. 21 divided by 7 is 3. That's why I've written this red 3 here. So that brings us to our very final answer. We have 3 times square root of 14 in the numerator over just 5 in the denominator. And again, the whole goal here is to rationalize the denominator. We wanted the denominator to not have a radical anymore, to not have a square root anymore. It's just a nice whole number. All right. Those two examples are there for you to come back to and refer to. Let's do 2 that are similar. And then we'll take a look at some MyLabs Plus examples. Rationalize the denominator. Okay, number 1, the square root of 13 over 5. Let's start by splitting this up into the square root of 13 over the square root of 5. Okay, if we're focusing on rationalizing the denominator, what we're going to do is notice the radical that's in the denominator, which is the square root of 5. And we'll multiply by the square root of 5 over square root of 5. Let's see how that will help. Okay, so in the denominator, the square root of 5 times the square root of 5 is the square root of 25, which is just 5 in the denominator. Let's multiply in the numerator. The square root of 13 times the square root of 5, that's the square root of 13 times 5, which is 65. So we end up with the square root of 65 in the numerator over 5 in the denominator. You might be wondering about reducing because you're maybe noticing the 5s. And 5 goes into 65. Can I do anything there? No, you can't. The 65 is sort of trapped under the radical. Okay, I know you're seeing the number 65. It's not really a 65. It's the square root of 65. Totally different. It's 8 point something. It's a decimal. So don't try to do any more reducing. We did as much simplifying as we can. We achieved the goal of rationalizing the denominator because our denominator is now 5. It's not the square root of 5 anymore. It's just 5. So again, our final answer is the square root of 65 over 5. Let's try one more in our notes here. Okay, number 2. 15 square root of 7 over 7 square root of 3. Okay, our goal is to rationalize the denominator. The radical in the denominator is the square root of 3. So let's multiply by the square root of 3 over the square root of 3. Don't bother multiplying by any whole numbers. Then you're just making big numbers and you'll have to reduce them later anyway. So that's not helpful. Oops. Okay, so again, I'm multiplying by the square root of 3 over the square root of 3. Let's do the denominator first. The square root of 3 times the square root of 3 is the square root of 9. So this is 7 square root of 9, which is really 7 times 3. I know that that's 21, but I'm leaving it factored for now because I have a feeling I might be able to reduce later. Okay, so once again, we had 7 square root of 3 in the denominator. We multiplied by the square root of 3. The square root of 3 times the square root of 3 is the square root of 9, which is just 3. So now I just have 7 times 3 in the denominator. Let's take a look at the numerator. 15 square root of 7 times the square root of 3. Okay, I just get to multiply those square roots together. 15 times the square root of 7 times 3. So that's 15 times the square root of 21. So 15 times the square root of 21 over 7 times 3. Before I put the 7 times 3 together, let's see if we can reduce with what's in the numerator, specifically with the whole number in the numerator, with this 15. Can 15 be divided by 7 or can it be divided by 3? If not, then we'll be finished. But yes, it can. It can be divided by 3. So let's take this 15 and 3 and we'll reduce. 15 divided by 3 is 5. So that 15 over 3 is really like 5 over 1. So finishing up, I now have 5 times square root of 21 in the numerator over 7 times 1 is just 7 in the denominator. Okay, and same thing as before. If you're wondering about the 21 and the 7 and can I reduce there? No, you can't because the 21 is under a radical, but the 7 is not. So in terms of reducing, focus on the whole numbers outside of the radical. Think of those as things you can possibly reduce and then leave the radicals where they are. And once again, our denominator is now just a nice rational number of 7. So our final answer again is 5 square root of 21 over 7. Okay, good. So we've seen some examples of multiplying, dividing, and then rationalizing denominators. I'm going to pause and take us to MyLabs Plus one more time. We'll see a couple more examples of some of these things, and then we'll be done. All right, so let's take a look at some more MyLabs Plus problems. So the last one we had done in the previous video, we had looked at some problems from 1 through 14. This is now number 15. This is a multiply and simplify problem. So multiply and simplify by factoring the square root of 6 times the square root of 21. As we saw before, there's a couple of ways you could do this. You could multiply together first and then simplify, or you can try breaking them down first if you prefer. Now 6 and 21, neither of them are multiples of perfect squares. So I think I will just go ahead and multiply them together. Let's see, 6 times 21 is 126. So this becomes the square root of 126. And now comes the simplify by factoring part. So again, have your list of perfect squares, hopefully starting to be memorized, but take a look at our growing list here. Square root of 4, square root of 9, square root of 16, square root of 25, etc. Now 4 doesn't go into 126, but 9 does if you try dividing. 126 divided by 9 is 14. So I can break that down into the square root of 9 times the square root of 14. The square root of 9 is 3. Now I know 14 is 2 times 7, but neither of those is a perfect square. So that's not really helpful. 14 is not a multiple of any of these perfect squares. It's not a multiple of 4, it's not a multiple of 9, and then when we get to 16, now that's too big. So I get to leave the 14 where it is under the radical, or under the square root, and our final answer is just 3 times square root of 14. Okay, and then when I get to problem number 16, it's the same idea but with bigger numbers. So this is still a multiply and simplify problem. This is the square root of 45 times the square root of 135. Okay, when I multiply those numbers together, I get 6,075. I'm not so interested in trying to break that number down, because it's just big. So I'd rather avoid that if possible. Let's see if we can break down these two separate radicals first. So let's focus on them separately, and then we'll keep the numbers a little more reasonable. So let's start with the square root of 45. We can break that down into the square root of 9 times the square root of 5, which is 3 square root of 5. Now 135, that's a bigger one. Let's see. Let's see if I can divide that by, let's see, I'm thinking 5. Let's see, if I divide by 5, that's 27, but I need to keep in mind perfect squares. Okay, time to make my list again. Square root of 4, square root of 9. Okay, I'll try 9. 135 divided by 9, there it is. Okay, so the square root of 135, I can break that down into the square root of 9 times the square root of 15. The square root of 9 is 3, and then I'll leave the 15 where it is. Okay, so here's what we have so far. We had the square root of 45 times the square root of 135. 45 got broken down into 9 times 5. The square root of 9 is 3, so that was 3 square root of 5. 135, we broke that down into 9 times 15. Again, the square root of 9 is 3, so we have 3 square root of 15. Let's put it all together. So 3 square root of 5 times 3 square root of 15. Multiply the outside numbers together. 3 times 3 becomes 9. Multiply the radicals together. 5 times 15 is 75. So I have 9 square root of 75. This is not going to be correct, but let's see what message we get if we type this in. So we're getting this message that we've probably seen before where it says, although your answer is equal to the correct answer, it is not in the correct form. That sometimes means I need to reduce a fraction more, or I need to factor more. In this case, I need to simplify my radical more. So, but at least I know I'm on the right track. It's equal to the correct answer, but just not in the correct form. So we're going to keep going. This just means the square root of 75 can be broken down more. So let's work on that. I think we've dealt with this number before. 75 is equal to 25 times 3. So the square root of 25 is 5. So when I break this down, again, the square root of 75, that's square root of 25 times square root of 3, which becomes 5 square root of 3. The 9 is also here. So we have 9 times 5 square root of 3. Putting it all together, 9 times 5 is 45. So we would get 45 square root of 3 for our final answer. Okay, let's try typing that in. 45 square root of 3. There it is. Okay, good. So that was number 16. Now, number 17, now we're getting into some dividing problems. So this one says divide and simplify. Okay, eventually it will say rationalize the denominator, but you don't need to do that immediately. You can, but you'll kind of go in a big circle that you can avoid. So divide and simplify. See if you can divide first. So this one is the square root of 40 over the square root of 10. Try dividing those first. Put it together as the square root of 40 over 10. 40 divided by 10 is 4. This just becomes the square root of 4, which is 2. So our answer is just 2. That's it. Okay, I'm going to make a small little comment here. This might not be an issue as you're typing, but what I've noticed in the past when students are writing things out, I've seen something like this. The square root of 4 equals the square root of 2. That's not true. The square root of 4 is just 2, which is not the same thing as the square root of 2. So just be careful. As you're simplifying a square root, the symbol will go away. Okay, so if you find yourself writing a lot of square roots where they maybe don't belong, just keep that in mind and be careful there. Okay, I believe the next question is similar. Yep, divide and simplify. All right, number 19 is the square root of a fraction. 25 over 81 is under the radical, so we would split that apart into the square root of 25 over the square root of 81, which is going to turn into just 5 over 9. So these are dividing problems where we can essentially just either divide or reduce, and we don't really need to do any of the rationalizing denominators yet. Okay, number 20 is similar. I'm going to move past that one. Okay, number 21 through the end of the assignment, now we are rationalizing the denominator. So here's number 21. It's the square root of 14 over 3. So here's what we would do. Rewrite it as the square root of 14 over the square root of 3. And then remember, to rationalize the denominator, we're going to multiply by whatever the square root is in the denominator. In this case, that's the square root of 3. So we're multiplying by the square root of 3 over the square root of 3. The square root of 3 times the square root of 3, it's the square root of 9, but we just get to write 3. In the numerator, the square root of 14 times the square root of 3. 14 times 3 is 42, so it would be the square root of 42. Now, it's a good idea to check if 42 can be broken down, and it kind of can, but it's not going to involve any square roots. Okay, so if you break it down into 14 times 3, and then 14 is 2 times 7, none of those are perfect squares, and there's no pairs of factors or anything. So I'm done at this point. Our final answer is the square root of 42 over 3. And let's be careful about how we type that. So if I choose to type, or to click on the square root first, 42, now to create a numerator of 3, or excuse me, a denominator of 3, if you click on the fraction button, that's not quite what we wanted, okay? So you have a couple choices. You can use the slash key, and then that will create a fraction for you. So I'm going to try to write out what I just did. Okay, so I'm trying to type the square root of 42 over 3. So square root button first, then 42, then the slash button, and then I can type 3. That's one way to do it with your keyboard. Another option, I'll go back and show this other option. If you know your answer will be a fraction, just immediately click the fraction button. And now my cursor is in the numerator. Now I can click the square root button and type 42. Now I can click in the denominator, or I can use my arrow key to get down in the denominator of 3. So just make sure your answer looks like how you want it to look. If the square root is too big or too small and it's not matching what you've written, go back and see if you can type it correctly. If you're having trouble, click Ask My Instructor or send me a screenshot or something and we'll try to figure it out. Okay, so again, with something like this, probably your best bet is click the fraction button first. Then when you're in the numerator, click the square root, type what you need to, then use the arrow key to get out of there and get down to the denominator where you put your whole number. So square root of 42 is in the numerator and then 3 is in the denominator. Okay, I'm gonna move ahead. Let's see, 22 and 23 are similar. 24 is similar. 25 is a little bit harder now. So let's take a look at 25. This is 10 square root of 7 over 7 square root of 5. So the radical in the denominator is the square root of 5. So that's what I'm going to multiply by. Square root of 5 over square root of 5. In the denominator, 7 square root of 5 times square root of 5. It's really 7 times the square root of 25. Which is 7 times 5, which is 35. So I have 35 in the denominator. In the numerator, we have 10 square root of 7 times square root of 5. That becomes 10 times the square root of 7 times 5, which is 10 times the square root of 35. So here's where we are. We have 10 square root of 35 over 35. This is not a final answer. I can reduce something. It's very important to understand where you can reduce and where you cannot. So leave the radical part alone. The square root of 35, you can't break that down at all. It's just 5 times 7. There's no perfect squares hidden in there. And so leave it where it is. What you can reduce is these sort of outside numbers, the 10 over 35. They have a common factor of 5, so I can divide them each by 5. The 10 turns into a 2, and the 35 turns into a 7. And maybe that's why I could have left it as 7 times 5 in that earlier step. 10 divided by 5 is 2. So either way, you end up with just 2 in the numerator with the square root of 35. So 2 square root of 35 in the numerator over 7 in the denominator. Let's see if we can type that. So I will click on the fraction button. In my numerator, it's 2 square root 35. Then I'll click to the denominator, and that is now 7. And so I have rationalized the denominator, because the denominator is a nice number and not a radical. So that was number 25. Number 26 and number 27 are very similar to that. There's not a whole lot of variety of problems we could choose from this textbook section. So you'll notice some repeated questions just to give you a little more practice. Okay, so we've made it to the end of our second unit. This is the end of lesson 31. I would encourage you to go back and take some of those optional quizzes. There's 3 that are in this unit that we're in. So let me pause briefly and remind you where those quizzes are, just for some extra review for you. All right, so we're just ending with a reminder of what our second unit is covering. So this unit is covering mostly factoring, but also square roots that we just saw. So it covers from everything from lesson 25 all the way through lesson 31, and that includes that quiz 11. And again, quizzes are optional. So homework 25, 26, 27, those are covered on quiz 9. So if you take that quiz, that's a good way to review those first 3 factoring sections. Homework 28, 29, and 30, those are all covered on quiz 10. So that includes special factoring, factoring review, solving equations by factoring, whereas quiz 9 was GCF, grouping, and then trinomials. And then the lesson we just finished, lesson 31 on simplifying square roots and rationalizing denominators, it's kind of its own topic. So it gets its own quiz. So quiz 11 is just more practice simplifying square roots and rationalizing denominators. So I encourage you to take any one or all of those quizzes. Each one you have 3 tries. They're optional, so the grade that you get doesn't help or hurt your standing in the class. It's just, you know, good review. And then on the day of our test, test 2 will show up right here after quiz 11. And then homework 32, that's in our next unit. So on the day of our test, test number 2, it'll be available in this list of assignments. And just like for test 1, make sure you're showing your written work and then submitting that as soon as possible when you're done with the test, ideally within, ideally just immediately, but within 1 hour of finishing. All right, well, I'm going to end here, and please let me know if you have any questions. Thanks.